Chapter 16, Single Factor Studies. In this chapter, we shall focus on the design and analysis of single factor studies. This includes the development of single factor analysis of variance, ANOVA model, the analysis and interpretation of factor level means, assessment of model adequacy, and the use of remedial measures when necessary. The single factor experimental and observational studies. Single factor experimental and observational studies are the most basic form of comparative studies used in practice. In a single factor experimental study, the treatments correspond to the levels of the factor, and the randomization is used to assign the treatments to the experimental units. So the relation between regression and analysis variance. Regression analysis, as we have seen, is concerned with the statistical relation between one or more predictive variables and a response variable. Both the predictor and response variables in ordinary regression models are quantitative. The regression function describes the nature of the statistical relation between the mean response and the levels of the predictive variables. Analysis of variance models are a basic type of statistical model. They are concerned, like regression models, with the statistical relation between one or more predictive variables and a response variable. Like regression models, analysis of variance models are appropriate for both observational data and data based on formal experiments. Further, as in usual regression models, the response variable for analysis of variance models is a quantitative variable. Analysis of variance models differ from ordinary regression models in two key aspects. The explanatory of predictive variables in analysis of variance models may be qualitative, like gender, geographic location, plant shift, etc. And if the predictive variables are quantitative, no assumption is made in analysis of variance models about the nature of the statistical relation between them and the response variable. Thus, the need to specify the nature of the regression function encountered in an ordinary regression analysis does not arise in analysis of variance models. Here we can view certain illustrations that we do with the regression and analysis of variance models. They are shown as normal curves. Now, the choice between two types of models. Regression analysis can handle qualitative predictor variables by means of indicator variables. When indicator variables are so used with regression models, the regression results will be identical to those obtained with analysis of variance models. The reason why analysis of variance exists as a distinct statistical methodology is that the structure of the predictor indicator variables permits computational simplifications that are explicitly recognized in the statistical procedures for the analysis of variance. The single factor ANOVA model. The basic ideas. The basic elements of the ANOVA model for a single factor study are quite simple. Corresponding to each factor level, there is a probability distribution of responses. The ANOVA model assumes that 1. Each probability distribution is normal, 2. Each probability distribution has the same variance, and 3. The responses for each factor level are random selections from the corresponding probability distribution and are independent of the responses for any other factor level. Note the normality of the probability distributions and the constant variability. The probability distributions differ only with respect to their means. Differences in the means therefore reflect the essential factor level effect, and it is for that reason the analysis of variance focuses on the mean responses for the different factor levels. The analysis of the sample data from the factor level probability distributions usually proceeds in two steps. First, determine whether or not the factor level means are the same, and second, if the factor level means differ, examine how they differ and what the implications of the differences are. The cell means model. Before stating the ANOVA model for single factor studies, we need to develop some notation. We shall denote by R the number of levels of the factor under study, and we shall denote any one of those levels by the index I. The number of cases for the ith factor level is denoted by Ni, and the total number of cases in the study is denoted by Nt, where Nt equals the summation from I equals 1 to N for Ni. For analysis of variance models, we shall always use the last subscript to represent the case or trial for a given factor level or treatment. Here, the index J will be used to identify the given case or trial for a particular factor level. We shall let Y sub ij denote the value of the response variable in the jth trial for the ith factor level. Since the number of cases or trials for the ith factor level is denoted by Ni, we have J equals I through Ni. The ANOVA model can now be stated as follows. Y sub ij is equal to mu of I plus the error of ij, where y sub ij is the value of the response variable in the jth trial for the I factor level or treatment. Mu I are parameters. The error of ij are independent normal with mean 0 and variance sigma squared, and I equals 1 through r as j equals 1 through ni. This model is called the cell-means model for reasons to be explained shortly. This model may be used for data from observational studies or for data from experimental studies based on a completely randomized design. The important features of a model. First, the observed value of y in the j trial for the ith factor level or treatment is the sum of two components, the constant term mu and a random error term, error of ij. Since the expected value of error of ij is 0, it follows that the expected value of yij is mu I. Thus, all responses or observations yij for the ith factor level have the same expectation, mu I, and this parameter is the mean response for the ith factor level or treatment. Since mu I is a constant, it follows that sigma squared of yij is equal to sigma squared of the error of ij, which is equal to the sigma squared. Thus, all observations have the same variance regardless of factor level. Since each error ij is normally distributed, so is yij. This follows because yi is a linear function of error ij. The error terms are assumed to be independent. Hence, the error term for the outcome on any one trial has no effect on the error term of the outcome of any other trial for the same factor level or for a different factor level. Since the error ij are independent, so are the responses yij. In view of these factors, ANOVA models can be restated as follows. Yij are independent, normal distribution with the mean of mu I and the variance of sigma squared. The ANOVA model is a linear model. ANOVA model is a linear model because it can be expressed in matrix terms in the form y equals x beta plus error, where y is equal to this matrix of y1, 1, all through y3, 2, and x is equal to this identity term. Beta is equal to the 3 mu's, and the error term is equal to all the error terms. We can see that the error of y is equal to x beta by computing the matrices. This indicates properly that the expected value of yij is equal to mu I. Hence, yij is equal to mu I plus the error of ij because it is given by y equals x beta plus the error term, which can all be combined. We can also see that the sigma squared of y is equal to sigma squared. Note the simple structure of the X matrix and that the beta vector consists of means mu I. When a ANOVA model is expressed as a linear model, it can be seen why it is called the cell means model, because the beta vector contains the means of the cells, here factor levels. The interpretation of factor level means. Observational data. In an observational study, the factor level means mu I correspond to the means for the different factor level populations. However, in experimental data, the factor level mean mu I stands for the mean response that would be obtained if the ith treatment were applied to all units in the population of experimental units about which inferences are to be drawn. Similarly, the variance sigma squared refers to the variability of responses if any given experimental treatment were applied to the entire population of experimental units. The distinction between ANOVA models 1 and 2. ANOVA Model 1 applies to such cases as a comparison of 5 different advertisements or comparison of 4 different Rust inhibitors, where the conclusions pertain to just those factor levels included in the study. ANOVA Model 2 applies to a different type of situation, namely, where the conclusions extend to a population of factor levels of which the levels in the study are sampled. Thus, the essential difference between situations where ANOVA Models 1 and 2 are applicable is that Model 1 is relevant when the factor levels are chosen because of intrinsic interest in them, and they are not considered to be a sample from a larger population. ANOVA Model 2 is appropriate when the factor levels constitute a sample from a larger population and interest is in this larger population. Thus, ANOVA Model 1 is also referred to as the fixed effects model, and ANOVA Model 2 is called the random effects model. In this and the next 2 chapters, we focus on ANOVA Model 1. For brevity, We omit the word fixed or model 1 and simply refer to the model as the ANOVA model. The fitting of the ANOVA model. The parameters of a ANOVA model are ordinarily unknown and must be estimated from sample data, as with normal error regression models. The method of least squares and the method of maximum likelihood lead to the same estimators of the model parameters μi in normal error ANOVA model. The notation. So as explained earlier, Yij represents the observation or response to the jth sample unit for the ith factor level. So the total of observations for the ith factor level is denoted by Yi, which is equal to the summation of j equals 1 through ni of Yij. Note that the dot in Yi indicates an aggregation over the j index. We can get the sample mean for the ith factor level by getting the Yi bar, which is equal to the summation of j equals 1 through ni of Yij over ni. That can also be simplified to be Yi over ni. The total of all of observations in a study can be y dot dot. That is equal to the summation of I equals 1 through r, the summation of j equals 1 through ni of Yij, where the two dots indicate aggregation over both the j and I indices. Finally, the overall mean for all responses is denoted by y bar dot dot. That is the summation of I times the summation of j of Yij over nt. That can also be simplified to be y dot dot over nt. And the two dots here indicate that the averaging is done over both I and j, the least squares and maximum likelihood function estimators. According to the least squares criterion, the sum of the square deviations of the observations around their expected values must be minimized with respect to the parameters. For a ANOVA model, we know that the expected value of observation Yij is the expected value of Yij is equal to μi. Hence, the quantity to be minimized is Q of the summation of I, summation of j, of Yij minus the μi all squared. That can also be written to be Q equals the summation of j of Yij minus mu of Y1j minus mu1 squared, all through the summation of j of Yrj minus mu r squared. Note that each of the parameters appear in only one of the component sums. Hence, Q can be minimized by minimizing each of the component sums separately. It is well known that the sample mean minimizes a sum of squared deviations. Hence, the least square estimator of μi is denoted to be μi hat, which is equal to the Yi bar. Thus, the fitted value for observation Yij for regression models is simply the corresponding factor level sample mean, where it is Yij hat is equal to Yi bar. The K down of degrees of freedom. Oh no, it is the residuals. Residuals are highly useful for examining the aptness of ANOVA models. The residual E of Ij is defined for regression models as the difference between the observed and fitted value. It is E of Ij is equal to the Yij minus Yij hat, which is equal to Yij minus Yi bar. Thus, a residual here represents the deviation of an observation from its estimated factor level mean. An important property of the residuals for ANOVA models is that they sum to 0 for each factor level I. As for regression analysis, residuals for ANOVA models are useful for examining the appropriateness for the ANOVA model. Now, the analysis of variance. Just as the analysis of variance for a regression model partitions the total sum of squares and the regression sum of squares and the error sum of squares, so a corresponding partitioning exists for a ANOVA model. The partitioning of SSTO. The total variability of Yij observations not using any information about factor levels is measured in terms of the total deviation of each observation. That is, Yij minus Y bar dot dot. When we utilize information about factor levels, the deviations reflecting the uncertainty remaining in the data are those of each observation Yij around its respective estimated factor level mean Yi bar. That is, Yij minus Yi bar. The difference between the deviations reflects the difference between the estimated factor level mean and the overall mean. Thus, we can decompose the total deviation of Yij minus Y bar dot dot into two components, where we have the total deviation equal to the deviation of estimated factor level means around overall mean plus the deviation around estimated factor level mean. Thus, the total deviation of Yij minus Y bar dot dot can be viewed as the sum of two components, which is what we just went over. When we square both sides and then sum, the cross products on the right drop out and we obtain this. The summation of I, summation of j, which is equal to Yij minus Y bar dot dot squared, which is equal to the summation of I of Ni times Yi bar minus Y bar dot dot squared plus the summation of I, the summation of j of Yij minus Yi dot bar squared. The term on the left measures the total variability of the Yij observations. So the SSTO is equal to the summation of I, the summation of j of Yij minus Y bar squared dot Y bar dot dot squared, which is the total sum of squares. And we can get the standing for the treatment sum of squares, which is equal to the summation of I of Ni of Yi dot bar minus Y dot bar squared. And finally, we can get the air sum of squares. That is the summation of I, summation of j, which is the residual of E of Ij squared. Briefly, it can be written as SSTO equal to SSTR plus SSE. The total sum of squares for analysis of variance model is therefore made up of those two components, the SSE, which is a measure of the random variation of the observations around their expected estimated factor level means, and the SSTR, which is a measure of the extent of differences between the estimated factor level means based on deviations of the estimated factor level means Yi bar around the overall mean Y dot dot bar. The K down degrees of freedom. Corresponding to the decomposition of the total sum of squares, we can also obtain a breakdown of the associated degrees of freedom. The SSTO has NT minus 1 degrees of freedom associated with it. There, altogether, the NT deviations of Yij minus Y dot dot bar, but 1 degree of freedom is lost because the deviations are not independent in that they must sum to 0, where the double summation of Yij minus the Y dot dot bar has to equal 0. The SSTR has R minus 1 degrees of freedom associated with it. And the SSE has NT minus R degrees of freedom. The mean squares. The mean squares, as usual, are obtained by dividing each sum of squares by its associated degrees of freedom. We therefore have the MSTR, which is equal to SSTR over R minus 1, and MSE, which is equal to SSE over NT minus R. Here, MSTR stands for the treatment mean square, and MSE, as before, stands for error square. The analysis of variance table. The breakdowns of the total sum of squares and degrees of freedom together with the resulting mean squares are presented in ANOVA, and the expected mean squares. The expected values of MSE and MSTR can be shown as follows, where we have the expected value of MSE equals the sigma squared, the expected value of MSTR equals sigma squared plus the summation of Ni of mu I minus mu dot squared over R minus 1, where mu dot equals the summation of Ni mu I over Nt. It is referred to as the weighted mean. Two important features of the expected mean squares deserve attention. First is MSE is an unbiased estimator of sigma squared. The variance of the error terms, not the factor level means mu, are equal. This is intuitively reasonable since the variability of the observations within each factor level is not affected by the magnitudes of the estimated factor level means for normal populations. Secondly, when all factor level means mu I are equal and hence equal to the weighted mean mu, then the expected value of MSTR is equal to sigma squared, since the second term on the right becomes 0. Hence, MSTR and MSE both estimate the error variance sigma squared when all factor level means mu I are equal. When, however, the factor level means are not equal, MSTR tends on the average to be larger than MSE, since the second term will then be positive.